My name is Anirudh and I'm here to explain the question 161 of the 2018 paper final exam, question number 9 for 5 marks. Question is as follows. Heat is flowing through an annular wall of inside radius Ri and outside radius R0. Thermal conductivity varies linearly with temperature from Ki at Ti to K0 at T0. Develop an expression for heat flow through the wall and show how it can be simplified when R0 minus Ri by R0 is small. Solution for this. First, the assumptions. First, I'm selecting my origin at the center over here. Temperature is not varying in this theta direction because this is symmetric. And it is here stated that temperature is varying from Ki at Ti to K0 at T0. This is the inside and outside radii. So I'm assuming that conductivity value is fixed at a certain radius. So if I take this radius over here, I'm assuming that the conductivity is same all across this entire length. And so if the conductivity is the same across the entire length, there is no temperature difference as well. Hence, the temperature properties are not varying along the length. Next, and it is also given that this variation is linear. Now my assumptions are that this is we are solving this problem at steady state and there is no heat generation or consumption or accumulation taking place. So first let's start with shell balance, which is input minus output plus generation minus consumption equals accumulation. Here, as we have defined it as per our assumption, these are 0 due to our assumptions and this is 0 due to steady state assumption. So we get input minus output equal to 0. Now I am denoting heat flux by QR, and heat energy at any point is area into the flux. So this is my area at the inner shell. This is my area at the inner shell, and this is the heat flux at that inner shell. This is my area at the outer shell. This is my heat flux at that outer shell. So substituting this, we get this 2 pi RL QR at R minus 2 pi R plus delta RL at QR and into QR at R plus delta R equal to 0. Now I'm dividing by the constant, which is 2 pi L delta R, and then I'm putting the limit delta R tends to 0. So we get this. Because this 2 pi L will get cancelled out, RQR will be left and delta R is the last constant is left under. Here also similarly, 2 pi L will get cut out and delta R will be left and R plus delta R will be left. Now when I limit delta R to 0, this will tend towards 0 and this will become RQR at R minus RQR at R plus delta R whole divided by delta R. This is the definition of first differential. So this will simplify to d of RQ by dr equal to 0. Now when you integrate this, since this is 0, the integration will give RQR is a constant C1. So we'll get QR is C1 by R. So QR equal to C1 by R. Now this question is only considering heat conduction and not convection. So QR can be taken as minus K dt by dr according to Fourier's law. Substituting this, you get minus K dt by dr is C1 by R, and it is given to us that thermal conductivity varies linearly with temperature. So I will write it in the form of y equal to mx form. That will be this y minus y naught equal to y1 minus y naught by x1 minus x naught into x minus x naught, which is the 2-point form of a of a straight line. This will be your slope of the line. So this will be y minus y naught equal to m into x minus x naught, which is the 2-point form. So when I substitute this, I get k minus k naught equal to k1 minus k naught by t1 minus t naught into t minus t naught. Now I will take this I will take this term over here as theta. This theta is not related to the angle, but this is just a variable theta. It is not related to the angle of the cylindrical coordinate system. So t minus t naught by t1 minus t naught is theta. So this equation can be rewritten as this: k minus k naught equal to k1 minus k naught into theta. But our equation over here is in the form of dt, so we need to find out d theta in terms of dt. Differentiating both sides, you get d theta is equal to dt by t1 minus t naught. So dt can be written as, by cross multiplication over here, we get t1 minus t naught into d theta. Now I can substitute this back over here, So I get, and I can substitute k as well. I can take this k naught to this side, and I can resubstitute this k over here as well. So this entire equation becomes minus of k naught plus k1 minus k naught into theta. This entire term is k. This t1 minus t naught into d theta. This entire term is dt by dr equal to c1 by r. Now I can integrate this. Now I can take this dr to the other side and I can integrate this. I will get 1 by r integration is ln r plus the constant of integration c2. And this side integration with respect to theta, this will give me k naught theta. This will give me theta square by 2. And I can take this theta out common over here. So make it k naught plus k1 minus k naught by 2 theta into whole, since I've taken theta out, theta into t1 minus t naught. Now the interesting thing to note over here is, if you simplify this, you will get 2 k naught plus k1 minus k naught. This will be useful later on, not right now. Now our boundary conditions, it was given that the temperature at the inner surface is Ti. So at radius Ri, you get temperature equal to Ti. So our variable theta now is T1 minus T naught by T1 minus T naught, which is 1. This is our first boundary condition. Our second boundary condition is that it is given that when temperature at the outside surface temperature is T naught. So at R equal to R naught, T equal to T naught, substitute this, you get our variable theta equal to 0. This is our second boundary condition. Now when you substitute both these boundary conditions into this equation, we get two equations. We can solve these for our two constants C1 and C2. Substituting the first boundary condition, you get this, and second boundary condition, you get this. Subtract these two and I get C1 from here as this. This is fairly straightforward. Now the thing that I was telling over there, interesting thing to note is this k naught plus k1 minus k naught by 2. If you simplify this, you get 2 k naught plus k1 minus k naught, which will become k1 plus k naught by 2. This term can be simplified as k1 plus k naught by 2. This is fairly simple. So now we have our C1 value over here, and and we are asked to find out how the heat is varying, which is only dependent on C1. So we can substitute this back over here. You get this. So heat flux at any radius is T1 minus of T1 minus T naught into k naught plus half k1 minus k naught by ln R1 Ri minus R naught in whole into 1 by R. Now the heat at any point is 2 pi RL into QR at that radius R. Substituting these values, QR at radius R is just R over here, and into 2 pi RL. So you have 2 pi RL into QR. This RR will cancel out. We can take this minus sign inside and make this T0 minus T1. So you end up with 2 pi L T0 minus Ti into K0 plus half K1 minus K0 by 2 whole divided by ln of R1 by R0. Now the interesting thing to note over here is there is no radius component in this. So the heat flowing is independent of the radius. This is again helping us show that our assumption that there was no heat generation is valid. Now we'll try, now for the second part of the question, we're asked to simplify when R0 minus Ri by R0 is small. So for that we'll have to simplify this term, because this is the only term involving R1 and R0. Now R1 by R0 I'm assuming as 1 plus epsilon, because you have the Taylor series formula expansion for ln of 1 plus epsilon or ln of 1 plus x. So this is your ln of Ri by R0 equal to ln of 1 plus epsilon. Using Taylor series expansion, you get this. Now when you simplify this and you try to find out what epsilon is, you get R1 minus R0 by R0. And our question states that this is very small. So you can neglect the higher. So in this Taylor series expansion, when you take e square, e cube, e power 4, these already this is small, so this will be even smaller. So we can neglect all of these terms. All of these can be neglected. So you'll get ln of 1 plus epsilon is epsilon. So you can substitute this back over here, and epsilon is this. So you end up with ln of R1 by R0 equal to epsilon, which is this. So you can substitute over here as R1 minus R0 by R0 over here. Substituting that, R0 will go to the numerator, R1 minus R0 will remain in the denominator, and this is your final Q expression. You simplify this, you end up with 2 pi R0 L, which is the area at the outer radius, T1 minus T0 by R1 minus R0, which is the temperature gradient, and this we already simplified as K1 plus K0 by 2, which is the average thermal conductivity. It's just an interesting thing to note. So it shows that as your Ri and R0 come closer and closer to each other, it seems to be tending towards the average conductivity of the shell. Thank you.